I'm going to demonstrate how to analyze an inclined member subjected to a distributed load that is projected onto the plane of that member. Say as opposed to a case where you have a distributed load along the member, such as its own weight. The example we're going to be looking at is example 4-15 in Hibbler on page 165 of the 7th edition of his structural analysis book, as shown here on the right hand side. First thing we have to do, just like we did on the last example, is check to make sure that we have the correct units, and we are in standard imperial units, so the problem is in standard imperial, so we're okay. The next thing we need to do is modify the grid. In this case, we have to do 2 spaces at 10 feet in the y direction and 1 space at 10 feet in the x direction. And so that's our grid. The next thing we need to do is create a member, and we do that by selecting the draw member. We don't have a truss element, so we don't do anything with this screen. We simply apply. We then connect the first two nodes to create that column, and then we go along an incline to create that incline member. We are done. And next thing we need to do is create the supports. In this case, point A is a pin support, and point C is a vertical roller support. Point B is a fixed connector, moment connected joint. So first thing we need to do is pull up the Modify Boundary Conditions button. We will do pin. And once again, in order to keep this problem in the 2-dimensional plane, we will fix any rotation or translation out of the plane. We will apply this to node 1, and then the next thing we will do is apply a vertical roller to support C. In this case, we're going to allow the vertical translation to be free. Apply that, and last thing we need to do is we need to ensure that that connection B stays in the 2-dimensional plane. So we will also release the X translation. One of the things that I didn't talk about in the last video is how to change the labels on the nodes. Let's do that for this case. Let me bring up the data entry menu, and we're going to go to joints, joint coordinates. In joint coordinates, I'm going to change N1 to A, joint or node N2 to B, and N3 to C, to be consistent with our diagram. So you can now see that the 3 points are labeled A, B, and C, consistent with our diagram. The next thing we need to do is apply the load. Actually, before we go on to the load, one easy way to check to ensure that you have the proper boundary conditions is you can see that the lines are thicker in the directions that are constrained. So for instance, in the case of support A, you have thicker lines in the horizontal and vertical direction. In the case of support C, you only have thick lines along the horizontal direction, which means that you will develop a reaction along the horizontal direction. And then the lines B are both thin. Okay, so with that out of the way, the next thing we want to do is apply the load. And normally, we will be working with either the Y, capital Y, or lowercase y. The uppercase Y coordinate is associated with the global coordinate system. It's indicated here. So if you apply a load in the global coordinate system, global Y, it would simply be just go down. As far as this loading, however, that will also be associated with a distributed load along the member itself, such as the weight of that member. In the case of, say, snow loads, you actually need a projected load. That's where the PY comes in. So for this particular case, we have a snow load. It's a projected load. So we're going to use P sub Y, not capital Y. If we had a pressure load along the member, then we would use the lowercase y to indicate that the load would be perpendicular to that member. So in this case, let us use PY, projected load. And we have a magnitude of 0.2 kips per foot. So we'll put 0.2, actually negative 0.2, 0.2. Doesn't really matter. So now we apply that. Notice that that load has been converted to an X load. So even though we applied a 0.2 kip per foot load, along the length of the member, it was translated into 0.141 kips per foot. That's how RISA handles this. In any event, the next thing we want to do is create a load combination. The load combination in this case is just going to be one load. We placed our load in basic load case 1, so we'll type 1 in there, and then our factor is 1. We can get rid of this window now. We can also get rid of the data window. And so we do then is solve the problem. And we can get rid of that. Okay, so we are now ready to do the axial force diagram, the shear force diagram, and the bending moment diagram. Let us do the axial force diagram. And so there's the axial force diagram. We have 2 kips of axial force in the column, compressive. And notice the axial force diagram along that inclined beam is not distributed in a triangular shape. Is not going to be constant. If we do our shear force diagram, simply going to use the show member results tool in this case. Along the Y, we have a shear force of negative 0.5 or 0.5, and then 1.1 and the beam, the maximum shear force. And then finally the moment along the Z. So we have a maximum moment of 5 kip feet in this problem. As we discussed in the last video, we can turn off the load. To do that, we can go into the set options for current view, and then we can go to loads and turn off the load. So there's a clean moment diagram. So if we were to change this to a capital Y load instead, what we would have to do is go back to the data entry, and then we would go to basic load cases. And in basic load cases, notice we only have one. So if we click on it, our member distributed load comes up, and we only have a piece of Y. If I change this to to Y, the problem is going to be a different problem. Now we have a uniformly distributed load along the member. If we do this, notice it asks if we want to continue with a new analysis, and we say yes, get rid of that. And if we solve the problem, notice we have a different moment, 7.1 versus 5. The difference again is now we have a distributed load along the entire length of the inclined member of 0.2 kips per foot versus the projected 0.2 kip per foot, in which case we got 5. I hope this was helpful.